I started reading Conway, John Conway's course in point set topology. I first found out about this book, someone I know, and he recommended it. He had used it. And so I've read the first two sections of chapter 1, and I'm in the third section right now, and the appendix. So I'll show the table of contents. The book is very well written. The typos that I've seen so far have been silly, like, you know, a space, an extra space after a comma, something silly like that. So it looks like it's a very high quality book, very well type proof. The first chapter, I'll just show the table of contents. It's got metric spaces. It's got topological spaces in the second chapter, and then continuous real value functions. It's only 3 chapters, and it's got an appendix that basically ends in Soren's lemma and Cantor's theorem, countability. The book reminds me a lot of Barlow and Sherbert in that the page size is deceptive. I'm doing about 2 pages of notes per page in this book, and it's a long read. And so I think it's going to probably take me, I'm going to say 6 to 7 or maybe 8 weeks to read the whole book at the current pace that I am at. The proofs are a little late. They're done a little different than the way, say, somebody like Mendelssohn does them, where in the case of Mendelssohn, he'll tell you exactly which theorems are used, and if you go back to those theorems, sure enough, you'll see the path. Here, Conway does not do that, and I actually like that because it forces me as a learner, as a student, to go back and actually find what are all the theorems that he used. So I'll give you an example from my notes. So in this case right here, in this theorem, Conway says, if X is in the closure of A, then there is a sequence A sub n in A such that A sub n goes to X. Well, he's really using Prop 1113b that says X is in closure of A, then there's a ball intersecting with A that is not disjoint. It's not the empty set. And then the next one, definition 12.4, says X is a limit point. Then proposition 127a takes you to there is a sequence such that A sub n goes to X. So that's a good example of how, and I actually like that about this book. It forces me not to be a lazy reader. If I want to know how each step was done, I'm constantly having to go back and look at the other theorems to find out where they came from. And I'm learning a lot by that. So yeah, so it's about 2 pages of notes per page of the book. I'll just briefly show my notes, but again, it's just the book as read. Of course, diagrams that are not in the book help me understand what is being proven. And I'll just, so sometimes I'll just draw all the different sets that are combined in a proof. So here's where I went to Appendix A, even though he recommended that you can read Appendix A when you get to Chapter 2. Then he started referencing it, so I was like, no, forget it. I'll just go read it. I'll just go read the whole thing. Things that you would find in most analysis books, all of them actually. Completeness, the real numbers, and then of course Soren's lemma is in the appendix. Used a little bit of ChatGPT here to figure out the difference between an ordered set and a partially ordered set. And so of course in a totally ordered set, all of the elements are comparable. In a partial order set, now not all elements are comparable. They don't satisfy A less than or equal to B or B less than or equal to A. Then, of course, some things that you find in other analysis books that I've already read, and this is something that I'm going to be careful about as I move forward because I'm doing multiple books. If I see something that I've seen elsewhere, like this is in Rudin, and other books, I make a note of it, but I'm not really following it exactly because I already understand it. So I'm like, all right, I'll put it in there, keep going. The same with the diagonalization arguments that I use for Cantor's theorem. I'm more looking for content that is done in a different way, or if I look at it and I've seen it elsewhere and I don't remember it, then I'll take notes again. Complete metric spaces, examples. So yeah, the book's got pretty good examples. It's got a very good methodology, very clean, and it's a long read, just as Bardo and Sherbert is per page. So you look at it and you say, oh, I'm going to read this book in a week. And it's like, no, that's not what's going to happen, at least not for me. Now, I'll just briefly mention that in the case of other analysis books, yes, they mention point-set topology, and even in Baby Rudin, he's got a whole chapter that he calls point-set topology, but the way he summarizes everything is very quick. Actually, and interestingly, I still have to find a place where K-cells are explained. And then in the case of Prodder and Murray, of course, I always call it Murray, like M-U-R-R-E-Y, but it's really Maury. It's another example where point-set topology is used, but it's kind of chopped up and found in different places. So for example, he'll have some basic point-set topology here, but if you look up in the book distance between a point and a set, he's got it in a chapter about approximations, or they, I should say. And then in the case of Wade is yet another good example, because in the case of Wade, Wade does all these concepts in point-set topology. Distance between 2 points, he never goes to the distance between a point and a set. It keeps it to actually 2 vectors, in this case. He does it all in R to the n. So yes, there are multiple analysis books that have point-set topology in them, but it's really nice to take the time and read through a book that is just a point-set topology. That's all it is.